Tu veux que je présente? No? Okay, so my pleasure to introduce Stéphane Jaffard. He will give 3 lectures, and this is the first one of the 3 about classification and detection of singularities of functions and signals, time scale versus time frequency methods. Stéphane is a professor at Université Paris-Est Créteil, and very pleased to give him to speak this talk. Thank you. Thank you for visiting us.
Okay, thank you, Jean-Marc. So is it okay?
Yeah.
Yeah. Okay. Okay. So last Friday I mainly talk on time frequency methods, focusing especially on the chirp how to detect the chirp generated by gravitational waves, and what are the quote good basis to detect these kinds of chirps. And what I would like in the next three talks is first to rather focus on time scale methods, and that by that we really mean wavelet methods to detect slightly different kinds of chirps. So I mentioned at least I showed some examples of this kind of chirps, like the one that you can see on the Riemann function, which can be characterized by conditions using wavelet coefficients. And then I will at the end of in the third lecture I will try to draw a bridge between the 2 approaches and see and explain what are the problems which are raised by trying to characterize chirps that are neither very well represented using time scale or time frequency methods, and how we can somehow mix the two approaches to have a kind of optimal way to represent that kinds of singularities. Okay, so I will. Okay, it looks like there's something which is blocked here.
Just click here and yeah, the screen's open. You just click once and yeah.
Okay, good. Okay, thank you. Sorry. Okay, so just to give you some kind of the data that we are interested in, we'll more focus on data that are everywhere irregular, and really the starting point of, for instance, multifactor analysis, of which I will speak a little bit today, and more tomorrow, is really turbulence data. So it's the kind of data that you can see on the top left of the screen. This is fully developed turbulence. So it's a signal which is captured in a big wind tunnel, and it's the velocity as a function of time at one point. So you don't have a full picture of turbulence, but you have somehow one-dimensional trace which is captured with a very, very high precision, and so that you have many scales available in the data to do analysis. Another very different type of signal is internet traffic signal on the top right. So this is very aggregated data. It's a number of bits per second, which are captured in a big internet node between Japan and the US. And on the bottom, these are three data which are captured on marathon runners. So this is a joint collaboration with Véronique Billat and Florent Palassin, which I mentioned in the first picture. So they're not mathematicians or signal analysts are really physiologists of sports, and they are interested in collecting either on marathon runners or other type of people doing sport, physiological data, and trying to understand what you can infer, for instance, on the way they handle their race by studying either separately or jointly. And this is really what I will talk about a little bit tomorrow and more on the third day, how to make a joint analysis of several data of different nature, but which are somehow correlated because they are captured on the same, in this case, on the same person at the same time. So here you see on the left the heart rate of the runner, the cadence of steps, and the acceleration. Okay, so one typical feature of this data is that they are everywhere irregular in some way, and we want to characterize this type of irregularity, classify it, and coming back to the main thread of these lectures, trying to put in evidence some kinds of very oscillatory behaviors, like the chirp behavior I showed in the first talk last Friday. And so please don't hesitate to interrupt me. Either you have the chat, Jean-Marc, or he is having a chat. Yeah. If there are some people online, I can. My strategy was to prepare a little bit too much slides so that I can adapt and focus on subtopics that you would be more interested in at some point. So don't hesitate to interrupt me. Okay, so the first idea is to try to measure the irregularity of such data, and it looks like they are everywhere irregular, but the irregularity can change from point to point. So first we need to define pointwise exponents, pointwise regularity exponents that will give some information on the local regularity of the signal and the behavior of the signal near near singularities. Okay, so we'll be interested in two types of regularity exponent. First, the classical regularity exponent, and then by comparing different regularity exponent, try to extract some additional information. And typically the additional information we want to extract is this kind of very oscillatory behavior that I showed on chirps. So there are several motivations for that. I mentioned one big motivation is turbulence, where you really expect. I showed some slides about that last Friday. You expect to find this type of very oscillating singularities. And in other, for instance, in physiological data and other types of data, you also want to put in evidence this kinds of behavior. Okay, we want to basically, I'll try to be in between mathematics and application. So you on the mathematical side, we are also interested in studying regularity properties of certain functions, certain stochastic processes, and determining both theoretically and then numerically on, for instance, on sample paths for stochastic processes, where you can find such behavior, such types of singularities. Okay, and this one main idea, one important idea is to express this information in terms of multi-scale quantity. So I will come back to this notion, which is very important. What is multi-scale quantity? And this is really related with wavelet expansion. So I will show that in the first simple example of a multi-scale quantity is the wavelet coefficients, and then we will see some more sophisticated ones which allow to characterize pointwise regularity. And finally, we are interested in working out, as I said, numerical methods which give some information on typically are some kinds of singles, which gives, I would say, not pointwise information, because this is really too precise to be put in evidence numerically, but rather some kind of quantitative information, like do some types of singularities show up in some data, and if so, do they show up often in some sense, or on exceptional sets? So basically, what are the sizes of the sets where certain behaviors show up? Okay, so I'll start with some classical regularity exponents, which have been used for a long time. There's been a lot of work on the local regularity of probability measures. So this won't be our main topic, but for a long time it's been mainly, I mean, the mathematics that were developed around the notions of pointwise regularity were really developed on probability measures. And so you can define pointwise regularity exponent for probability measures. I don't know why I put some absolute value around mu. If it's a probability measure, it's positive, but anyway. We say that a probability measure belongs to M alpha. If you can bound the mass of a ball centered at x naught and reduce r by c r to the alpha. And what is this is a misleading name, but I mean the traditional denomination for the corresponding pointwise exponent is a local dimension at a point, and it's just basically the best possible alpha that you can pick in this definition. So for instance, if you have the most irregular probability measure is just a Dirac mass at a point x naught, and in that case, the best exponent you can use, and you can use here is alpha equals 0, so you will get an exponent which is just 0. If you have the Lebesgue measure, which is basically the smoothest measure you can think of, you will get exactly, I mean, this will be just r to the d, so you will get a local dimension which is d. And for instance, you can have nice intermediate cases. So for instance, if you consider the countermeasure on the triadic counter set, let me just remind you the construction of the countermeasure on the triadic counter set. You start with, you put the uniform measure on the segment 0, 1, and then you say that basically you shrink the measure so that the first interval of length 1/3 has measure 1/2, and the last one has measure 1/2 also, and there is no mass in the middle. And then basically you continue this construction, so you will have here a little interval of length 1/9 and measure 1/4, and they all have the same measure. And then you continue, and at the end you have the singular measure on the interval 0, 1, which is a countermeasure. So in that case, if we have let me just show you how to determine at a point of the counter set what is the local dimension. If you have a point, you have this sequence, you have a sequence of intervals which contain your points x2, and at the nth generation, this point will be contained in an interval let's write it I and k. So n is a generation and k will be the position of the little interval, which will be of length 3 to the minus n, and the measure of I and k will be 2 to the minus n. So we try to write the measure as the power of the interval. So clearly 2 to the minus n is equal to, you have to write I and k to the power log of 2 over log of 3 to that's correct. So you see that the in that case, at the point of the triadic counter set, the local dimension of the measure is log of 2 over log of 3. Okay. This is I just mentioned cities as a good example of kind of singular measure, a little bit like the triadic counter set, but 2D and somehow not as regular, but more kind of random distribution. But if we consider, for instance, the distribution of population inside a city, basically you would like to model it like a mass distribution on the kind of random counter set. Okay, and actually we have a joint project with people in urbanism and geography, in which we are interested in studying quantities which are supported by such fractal sets. Like you want to study the repartition of populations, the water consumption, the energy consumption, the measure of different measures of pollution. And I will come back to that at the end, because you want basically, I mean, it's interesting to study each of these data independently, but it's more interesting to study them in a joint way and to understand how they are related. Okay, so when I will talk at the end about maybe tomorrow about joint multifactorial analysis of several data, this is the typical example we have in mind. Okay, so these are the cities. So basically, at the top, it's really the set, the support of the measure, and at the bottom you have the repartition of population of different cities, which are different from the one on the top. Maybe I should have picked the same ones. Okay, so you see, these are examples at the bottom of these kinds of measures supported by a fractal set. One difficulty to study this type of data is that as I said, it's not as nice, as regular as typically a counter set, which looks everywhere the same. And also the characteristic of the fractal set change. For instance, is you would like to model that by a counter set which is not 1/3, but is much larger in the center and is much sparser on the if you go far in the suburb. So this raises very quickly difficult mathematical problems to know what are good fractal sets, which basically changing parameters depending on the location, and then analyzing data supported by these kind of strange fractal sets. Okay, so first I was mentioning that these type of measures are supported by fractal sets. And so what can you say about, first you would like to say something about the support, I mean really the set which supports the data. And so you have a kind of exact self-similarity in the case of the counter set. Let me maybe just come back to here. You see that at the end, if you pick, for instance, the first third of the counter set, the whole counter set shrunk by 1/3 exactly, and same for the right hand side. But so this is exact self-similarity in some way, and here you don't have, of course, exact self-similarity for such sets. So you would like to have a way to estimate this self-similarity, which is not exact, but is kind of adapted to more random geometry typically. So a good way to measure to associate some kind of self-similarity exponent to such sets is to associate what is called the box dimension to this set. So basically, you pick a parameter epsilon, so it's a length, it's a scale, and you call n of epsilon the minimal numbers of balls of radius epsilon, which you need to cover the set. And if you basically you make a log plot regression. I mean, you try to write n of epsilon as a function of the scale with a certain exponent. So I mean the precise mathematical definition is you take the log of n of epsilon, you divide by log of epsilon, and you take a limit minus a limit, and you get this upper box dimension, to be precise, because we take a limit. So one advantage is that you can compute that on experimental data. And for instance, a picture I took from a book by Pierre Frankhauser, who is a French specialist of urban geometry, who comes from theoretical physics. So he has a lot of intuitions coming from theoretical physics. Is that if you, for instance, this is the Paris region, and if you do this log plot regression, you see that you have a really a nice line on the long on a fairly large number of scales. So it really means that it's a good approach.
Stéphane? So the black spot here, the black region, what does it represent exactly?
So this is this is just the how do you call that in English? In French, it's le bâti, the construction. Okay, the construction. Except that this is not very good. I mean, it's not fully, but okay. This is.
So what about the type of construction?
Yes, yeah. As soon as you have a building, you see, okay, you have the support. Exactly. Yeah, because you cannot say, one difficulty is to interpret the data. I mean, if you have just, it's easy to have satellite pictures. I mean, this is an old, this is a fairly old, I mean, it's not very old. The book goes back to the 80s. Now we have a very precise data, but it's hard. One of the problem is it's hard to fit the pictures. You have some information, for instance, satellite information, precise satellite information about the buildings. You have information about population, but it's not given by satellite pictures. So you have fitting the two is kind of difficult. Okay, so this was just a few words about measures and the set carrying measures. Now I come back rather to functions, and the classical way to measure pointwise regularity exponents for function is by using the pointwise Hölder regularity. So I will come back to this definition, and we'll discuss it in details, because there are other ways to measure pointwise regularity, and you can extract very interesting information by comparing these different ways to measure pointwise regularity. But let's first start with basically the most simple and the most commonly, by far the most commonly used notion of pointwise regularity, which is pointwise Hölder regularity. And so the definition is that the function belongs to C alpha if the function minus basically its Taylor expansion is bounded by C x minus x naught to the alpha. And as usual in the definition of pointwise exponent, you take basically the supremum of all alphas for which you have this estimate. Okay, so this is okay as soon as the function f is, for instance, locally bounded, and this is important because one of the motivations for switching to different exponents is to have definition which makes sense when the functions are not locally bounded. But first we start with locally bounded functions. So typical pointwise singularities are what we call cusps. So like something like x minus x naught to a certain power, and then the exponent at x naught of this function is exactly h. And what we'll call chirp. So this is not exactly it doesn't look exactly like the chirps I was mentioning last Friday, but it's the kind. If you look at pointwise singularity, this is the typical singularity. So if you consider x minus x naught, and you make a very strong vibration by, which gets stronger and stronger as you get towards the singularity, by multiplying by a sine 1 over x to a certain exponent. You have another singularity which really does not look like the previous one, but has the same order exponent. Okay, so in the example I showed, it's 1/3 in both cases. And one of our problems will be to see how we can draw a difference. Not just by looking, but by having some mathematical tools which will allow to draw a difference between these two types of singularities. In particular, because we will be interested in deciding if there are singularities like the second one in data. So just to give you a flavor of what Hölder exponent means, these are functions which have a constant Hölder exponent, so their regularity is everywhere the same. So actually, it's sample path or fractional Brownian motion. So it's if you know a little bit of probability, it's you start with the Brownian motion, which corresponds to 1/2, so that's the sample path in the middle, and you take a fractional integral or fractional differentiation. So if you integrate, you go towards the bottom and you have smoother and smoother function. And if you take a differentiation, you go up and you have a rougher and rougher function. So this is just to give you some idea of to which roughness in some sense corresponds the Hölder exponent. And all of these are between 0 and 1, because if you go to exponent larger than 1, you don't see anything on the picture. The curve looks smooth and you don't see any difference. So this wave function with a constant regularity, everywhere the same regularity. And these are functions which varying regularity. So these are examples that were constructed by Daoudi, Jacques Lévy-Vell, and Yves Meyer. So there are several ways to construct such functions. The first one is a kind of Weierstrass function with a varying exponent in some way. And the second one is constructing using a wavelet construction. Okay, so just maybe to have a small exercise, we can consider the Deville staircase. So the Deville staircase, if you remember the measure we constructed here, the canonical measure carried by the triadic counter set, we can consider the function, the characteristic function, which is just basically the primitive of this measure. So you write f of x, this is the interval 0, 1. F of x is the measure of the interval 0x. Okay, so this was called by Benoit Mandelbrot the Deville staircase, and it's a nice function which looks like a staircase, but the sizes of the stairs are very, very irregular. And so this is clearly a locally bounded function, so we can compute its Hölder exponent, and basically what you see is that if you are on an interval on which the function is constant, of course the value of the Hölder exponent is 0 because the function is locally constant. And if you are at a point x0 on which the function which belongs to the triadic counter set, then what happens is that this is because of this definition, this will really be the increment of the function between the beginning of the end of the little triadic interval, which contains the point x0. So in the neighborhood of x0, you will have 2 points on each side. Let's call them y and z, such that f of y minus f of z will be equal to the length of the interval, so 3 to the minus n, and the length y minus z will be 2 to the minus n here. So the increment of the function is the measure of the interval, and on the side of the interval is 3 to the minus n. So if you want to write this increment as a power, the increment of the function as a power of the increment of the variables, exactly the same computation will give you that f of y minus f of z will be y minus g to the same exponent. I'll call it alpha here. Alpha. So that will mean, and this is clearly best possible. So it means that the older exponent at the points of the triadic counter set will be again log of 2 over log of 3. Okay, so this is just to show you on a simple example. Now we can compute older exponents. Now a slightly more complicated computation, but okay, no, time is going fast, so maybe maybe I would like to say a few words about Weierstrass function, because it shows in a nice way how you can estimate older exponents, and it really shows why wavelet methods show up naturally to analyze such functions. So let's consider this function. I pick an h between 0 and 1. And okay, how can we compute the older exponent at every point? So okay, the easy part is to prove regularity. Okay, and how do you prove regularity? You write wf of h minus wh of y. So that will be a sum of 2 to the minus sj. Did I write it with cosine? I mean, it doesn't make a difference, but yeah, cosine 2 to the jx minus cosine 2 to the jx y. And okay, so basically you have two ways to estimate these. One is to just to use the mean value theorem, which will tell you that, so you have two ways. Either you can bound this by using the mean value theorem, 2 to the j x minus y times the supremum of the derivatives of the cosine, which is 1. So you have one bound, which is that. And another possibility, which is I would say the trivial one, is to say that, okay, I bound this by 1 and this by 1, and so I can bound this by 2. Okay. And so now when you want, okay, yeah, this is not a good idea. Okay, so if now we want to bound this in absolute value, and clearly if j is small, okay, x1, y are fixed. If j is small, let's say that of course x minus y is small but fixed. So first, for the first j, this will be small, so it will be a good bound. But of course, it increases with j, and at some point it will get worse than that. So the only trick is to say, okay, I'll take the best of the two estimates to estimate the function. And so we just determine when we fall from one case to the other, and that will be when this is of the order of magnitude of 1. So we'll call will introduce a capital J, which is defined by the condition that 2 to the j x minus y, let's say, is between 1 and 2. Okay, so this defines a unique J. And in the estimate of this, I bound it by a sum. So first I stop to capital J. I use the first estimate. So I have the 2 to the minus 8j here, plus the sum of the remaining terms. And then I just bound the difference by 2. So I have a 2 here, 2 to the minus sj. Okay. So now this goes out of the sum. Here I have 2 to the 1 minus hj x minus y goes out. And here I have a partial sum of a geometric series, which is increasing because h is strictly between 0 and 1. So its order of magnitude of up to a constant is the last term. So this will be bounded by x minus y, 2 to the 1 minus h capital J. Something wrong?
Infinity?
Oh, no, to J. Okay, sorry. And for J plus 1 to infinity, here I have this time a decreasing geometric sum, so up to a constant. So here I have constant, which I don't compute. It's of the order of magnitude of its first term, and I have the 2 to the minus hj. Okay. So here comes the definition of 2 to the j. So basically, I can replace 2 to the j up to constant by 1 over x minus y. So I have here x minus y. 2 to the j, yes, is 1 over x to the minus y. So here I have 2 to the 1 minus h. Sorry, I have 2 to the j, which is 1 over x minus y to the 1 minus h, plus 1 over x minus y to the minus h. And now here we have x minus y, which simplifies with the 1 over x minus y to the 1. I have 1 over x minus y to the minus h, so that x minus y to the h, the first term. I have constant here. And here it's the same, so I have 2 times this. So this shows that you have a uniform regularity, and this is really very, very simple. I mean, the only trick is a little trick I showed at the beginning. So now in some sense, the hard part, and this is where Weierstrass had problems, and he had to make some additional assumptions, is really to prove irregularity, to prove, yes, irregularity. And why? Because when you consider increments of this function, you see you have this function, these cosines, which are oscillating very, very fast, and you want a lower bound on something which is oscillating very fast. So that's not easy. And this is really the part where there is a nice wavelet trick, which I would like to just to show you. And basically the wavelet trick is, sorry, yes, the bottom here, the fact that we'll consider a continuous, what we call a continuous wavelet transform of the function. So a wavelet for us right now in the continuous case is just a function with a smooth, well-localized function, which has at least one vanishing moment, because we'll consider exponents of regularity between 0 and 1. So one vanishing moment will be enough. So I need at least this decay for the wavelet. And the continuous wavelet transform is defined this way. You it's a function of two variables. You have a scale and a location, and you just take a convolution of the function you started with dilated and contracted versions of your wavelet. And I'm not sure how far did I? Okay, no. Okay, so the point is that if a function is smooth at a point, then necessarily its continuous wavelet transform has to decay with a certain rate when the scale goes down to 0, A goes down to 0, and B is close to that point. Okay, so more precisely, we have a little proposition which says that if F belongs to C alpha at x naught, then necessarily the continuous wavelet transform is bounded by a constant A to the alpha plus B minus x0 to the alpha. Actually, we'll need that only for B equal x naught. So I'll just, this is, you can remember that on the proof is always the same, but maybe to be a little faster, I will prove just the second point, which is sufficient for Weierstrass function. In particular, we have that CF of A and x naught is bounded by C A to the alpha. So I take B equal x naught. So if you are just above, for B equal x naught, just above the point x naught, you have this decay. And all the trick, first I will prove that it's a 3 lines proof. And all the trick then is to find the good wavelet so that you can very easily show that this is quite big. This is larger than something, so that the function cannot be smooth. Okay. And so what is a good wavelet in the case of the Weierstrass function? It's a wavelet that will pick just one frequency. And then this will eliminate the problem I was mentioning of having all these piles of frequency that can compensate and make increments of the function may be small when you would like to show that they are big. Okay, so this, if I am in the Fourier domain, this is my next picture with a nice picture of Fourier. What I pick, so the frequencies of the Weierstrass function are 1, 1/2, 1/4, 2. The one I picked, okay, with dyadic frequencies, 4, 8, and so on. And the idea is to pick in the Fourier domain a wavelet which is something like that. Okay, so basically you pick just here the frequency 1. And if you shrink and dilate it, you will always, so I pick a support which is close to 1, you will never pick two frequencies at the same time. If you dilate it or contract it, you will always pick at most one frequency. So I pick a wavelet psi hat like that. And if I compute the, so let me come back to the definition of the continuous wavelet transform. Okay, if I compute the continuous wavelet transform using this wavelet of the Weierstrass function, what I will get is C of A and B is equal to 1/A, the integral of the sum of 2 to the minus S J cosine 2 to the jx psi of x dx. And I'll see what's happening for particular psi of x minus b over a. And I want to see what's happening for b equal x naught. And I will pick also just the frequencies a equals 2 to the minus j. Okay. So in that case, I will have 1/A will be 2 to the j, I can, okay, you can check that you can invert sums and integrals here. So we'll have 2 to the minus sum of 2 to the minus 8j. Here I have the integral of, okay, I'll just write that, cosine 2 to the jx psi of x minus b over a dx. And I make here a change of variable u equal x minus b over a. So here I have, okay, let me write that. Or I use the second blackboard. I make this change of variable. So x is au plus b. So I have a 2 to the j sum of 2 to the minus a j. The integral of cosine 2 to the j au. A is 2. Okay, I'll keep a for a moment, which is simpler. Au plus b psi of u. And the dx is a du, so this makes this disappear. Okay, and now you can recognize writing the cosine as the sum of e to the ix minus e to the minus ix over 2. What I get is just the sum of 2 to the minus sj times the Fourier transform. Oops, I have a factor 1/2, which I can, which we'll forget. I mean, all this is up to constant. The Fourier transform of psi at the point 2 to the j a. And there is e to the, I'll write it for a moment, which is of modulus 1, so it won't play a big role. And now the point is that since I pick a equals 2 to the minus j, this is 2 to the j, 2 to the minus capital J. And this is where is the important point. Because of this picture at the top, all these exactly vanish except one for little j equals capital J. So now you don't have to deal anymore with compensations. You just have one term. And that's, so this is, you just have one term corresponding to little j equal capital J. And then you have psi out of 1, which we can decide is 1. And then a term of modulus 1. So if I take a modulus, I have exactly this. Okay? So
Capital J is sorry, capital J is any integer.
Yeah. So I pick for A 2 to the minus j. Okay? So then for C of 2 to the minus j at a point, actually this is at any point B, you see. So in particular at B equals x0. Is exactly of this order of magnitude. And this shows you that the regularity cannot be better than capital H, because you have exactly this size of the continuous wavelet transform for this particular point and this particular scale. So this shows you that the Hölder exponent at any point has to be smaller than capital H. And since we prove that actually we have uniform regularity, function is CH. This proves that at every point it is exactly capital H. Okay, so this is really how to and this trick is this kind of trick is very standard in wavelet analysis. The fact of basically using the miraculous wavelet in some way that completely trivializes a computation. So I would like, yeah, I'm going much more slowly than I thought. I would like just maybe to give you some idea of what can we say for functions which are a little bit different from Weierstrass function, and for instance the Riemann function that I was mentioning last Friday. So we have 1 over n squared x. So actually, the tradition, which I think is right, is that at the time when people were not sure that there could exist continuous nowhere differentiable function, Riemann would have proposed this function as a possible example of continuous nowhere differentiable. So it's clear that a series of function which is uniformly of continuous function which are uniformly convergent. But okay, actually, so the tradition said that Weierstrass tried to use this example, could not, because the frequencies are not. It's what we can call a lacunary Fourier series, but the frequencies are not lacunary enough, and it changed n to the square by sequences that grow in a geometric way and could prove the theorem. Okay, but if we come back to this example, we might think, okay, can we adapt the proof that I gave here to show? I mean, it's the proof I gave to prove regularity. You can use it, and you will get exactly by the same trick of splitting into two sets of frequencies, low frequencies and the high frequency. You will very easily show that this function is C1 half, okay, uniformly. Exactly same proof. Okay, now you want to prove irregularity everywhere. Okay, so actually the answer is that you don't have such a nice answer as for Weierstrass function. The regularity depends from point to point, but you want to adapt this idea and see what it can yield. Okay, so now the situation is not as good as here because we don't have these frequencies with increased geometrically. We have the n squares, okay, instead of having the powers of 2. So we have 1, 4, 9, and so on. So the point is, if you try to use the same trick, you won't be able to use it, because just by dilating psi hat, because the squares don't grow fast enough, you will you will catch several frequencies and you won't be able to say anything. So the next idea, and this is an idea to which I will come back at the end of the lecture, is just to adapt and to say, instead of just dilating the Fourier transform of psi, I can dilate it. I will dilate it and translate it, okay, as much as I can. For instance, if 16 somewhere here, okay. So if I have here n square, n plus 1 square, n minus 1 square, what I can do is, okay, bring it here so that it just covers, keeps the same idea, it just covers one frequency, but I make it as wide as possible, just to try to mimic this, okay? And so what you are really doing here is you are not just dilating the wavelet, so it's not exactly a wavelet transform, you are dilating and translating the psi hat. And so this is something I would like to come back at the end of the lectures. You are considering a transform which is more sophisticated than the wavelet, the continuous wavelet transform. You are adding an extra parameter here because you are also shifting in frequency. Okay, so you are taking a transform in which you translate the wavelet, you dilate the wavelet, and you shift in frequency the wavelet. Okay, to get again to get as much as possible of this proof, and then basically using just the same ideas. What you will get here, in this case, I mean, you can prove a general theorem about, you know, some Fourier series having some lacunarity. I think so what we call lacunary non-harmonic Fourier series. Okay, I don't want to talk too much about that. But just come to the point. The same proof, exactly the same proof, but using this more sophisticated transform, will tell you that this function is nowhere better than smoother than C2. Okay, so you have a basically a big gap, C2 at a point X. Okay, so at no point, all of the exponents are between 1/2 and 2. Okay, so this is what we will get just easily by the same trick. So what you can prove using a more sophisticated wavelet method is that all of the exponents are actually between 1/2 and 3/4 in this interval, H, and you have exceptional points, fractional points, where it goes up to 3/2. So this disproves actually Riemann's intuition that it was nowhere differentiable. There are points where the older exponent is larger than 1, so the function has a derivative, and it's even a little bit better because the exponent is 3/2. But it's not 2. Okay, so what we get by this method is probably not optimal, and this is I want to finish this first lecture by this question. It's really an open problem, a nice open problem on a very simple open problem on a trigonometric series. So here you can prove a very sharp result, and you can determine the regularity at every point because you have exactly this set of frequencies and this coefficient. So that means that for another magical wavelet, you have a wavelet transform, which is I don't want to go into the detail, which is the Jacobi theta function, and you can estimate its size at every point, and using the theorems I mentioned on which characterize pointwise regularity by the size of the continuous wavelet transform, you can determine exactly the elder exponent at every point. But now assume that you have a series like that with sine n square x, but you have coefficients an, which are not the magical coefficients for which you can do computation, but you just assume that the an are of the same order of magnitude, okay? But not the perfect one. So same proof, exactly same proof. We tell you that this function has older exponents between 1/2 and 2, because we never use the fact that it's exactly 1 over n squared. Okay, so h. Okay, but I assume I now take a Fourier series, but I just assume that the coefficients are not exactly 1 over n squared, because for this function I can say everything, but are of the order of magnitude of 1 over n squared. So they are between a constant over n squared and another constant over n squared. Okay, I can put the square inside or outside, it doesn't change. Okay, so same proof, same shows that, and this is optimal, of course, because we know that for the Riemann series, there are points where the exponent is exactly 1/2. The question is this optimal? In other words, this very simple proof that I gave, does it give you actually an exponent that can be reached? Can you find out some Fourier series for which by finding very tricky an, you can have points which are even smoother than 3/2 and go up to 2? Or is this proof not optimal? And can you show that for such a series, actually the older exponent is maybe a 3/2 could be the best possible? We know that for some of them it can be 3/2. Okay, this is something. This is a very simple problem on which we don't know how to deal with. Okay, okay, I'll stop here. I wanted to to show you this method because as I said, I'll come back to that in the last talk. The idea of having a very sharp analysis by having this time scale frequency analysis and trying to understand what's happening when you do this both time and scale and frequency is something which is not clear to us, but there are a few examples like that where we can see that we have to do this type of analysis to get some results. I mean, standard wavelet results for such functions would not tell you anything. I mean, good wavelets will never be able to unravel the irregularity. Okay, so I'm sorry, I went a little bit over 1 hour. I'll stop here, and tomorrow we'll go into the classification of pointwise singularities.
Thank you, Stéphane. Not sure there is some comment in the chat, so we will resume on tomorrow.
Okay.
Thank you.
Thank you.